Okay, so today we will work through the practice problems and let's see what's the best way to do it. I have them on my iPad also, so I can just open them here. Okay, it might be more efficient if you all have the Google Drive open with the problems. Otherwise, I will have to do back and forth because there is the figure also. Yeah, so we have 1, 2, 3, 4, 5, 6 problems. Let's start with the first one for sure. And then the others, I might differ in the amount of detail in every problem, but the first one I want to do in full. So this one asks us to look at this figure, which is provided in the folder over here, and it wants you to think about why is, and I think Abby asked this question, why should B be adiabatic? So the other way of putting this is, if you're going from P1, V1, T1 to the same volume, there are two processes. So let's draw this in the notes. So problem 5, another way of thinking about it is that you have two processes going on. The first of them, let me open it on my screen. Takes you from pressure, volume, temperature P1, V1, T1 to P2, V2, T1. And this one takes you to P3, V2, T2. So both of them have the same volume. And this is on the pressure volume plot. And you have been given this information that one of them is isothermal and the other one is adiabatic. And basically you have to rationalize as to why should A be isothermal and why should B be adiabatic, or rather why should they lie below each other? Why should not B be on top of A? So anyone knows how to proceed in this? Any ideas? So the thing to keep in mind here is an isothermal process. This is a perfect gas, first of all. None of this would apply if it was a real gas or a generic gas, because we are working only for perfect gas. The equation of state always applies. For an isothermal process, we know that PV is equal to nRT, means PV is equal to constant. In other words, isothermal process must follow P1 V1 is equal to P2 V2. And that's the plot you have seen over here. This red thing corresponds to PV is equal to constant. So pressure times volume, this inverse relation, this is an hyperbola. It just looks like this. That's what you have seen over here. The more important question is why should the adiabatic process be below it? For adiabatic process, the equation of state still applies, but now we can still say P is equal to nRT, but that doesn't really help us, right? Because pressure is changing, volume is changing, temperature is changing, everything is changing. So this is of no help. For an adiabatic process, this problem is slightly complicated because if you forget everything, you have to go from scratch and derive. But we did this in class that PV to the power gamma is equal to constant. And the thing to remember here about gamma is that yeah, nRT is not constant. PV is not constant. I'm not making any claim about T decreasing or increasing. That's what you're trying to prove, that what's going to happen to T. So we don't have any claims, but we just can't use the equation of state applies, but it's useless. So we have to use PV to the power gamma is equal to constant. This is what we derived for an adiabatic process. How did we derive it? Recall, we set dq is equal to 0, so du is equal to dw, and if it's a perfect gas, that means cv dt is equal to minus pdv, and here we substituted cv dt is equal to minus RT by V for 1 mole dV, and then we integrated both sides. Integrated both sides, and that we got it. So this operation for an adiabatic process is something which should be at top of your head. You should be comfortable with this manipulation, and with this you can get a relation between V and T. But now you can introduce, instead of T, you can introduce P, and you get PV to the power gamma is equal to constant, where gamma is equal to Cp by Cv. So what does this mean? So on the first hand, we have P1 V1 is equal to P2 V2, and this PV to the power gamma is equal to constant means that this adiabatic process must follow P1 V1 to the power gamma is equal to P3 V2 to the power gamma, right? We don't yet know whether P3 is more than P2 or P3 is less than P2 or P3 is equal to P2. We are trying to prove that P3 must be less than P2, right? That's what we are trying to prove here. If P3 is less than P2, we are done. So how do we do that? So adiabatic process implies P1 V1 to the power gamma is equal to P3 V2 to the power gamma. And at the same time, we have P1 even equals equal to P2 V2. So take equation 1, take equation 2, and divide both sides. So write down P1 V1 by P1 V1 to the power gamma is equal to P2 V2 by P3 V2 to the power gamma. P1 V1 cancels. We are left with V1 to the power 1 minus gamma is equal to P2 by P3 multiplied by V2 to the power 1 minus gamma. Therefore, we get P3 by P2 is equal to V2 by V1, 1 minus gamma. What do we know about Cp by V1 by V2, 1 minus gamma is V2 by V1. So this is equal to V1 by V2, gamma minus 1. What do we see here regarding V1 and V2? It's an expansion. So that's clear that V1 by V2 is less than 1, right? That is given as per this plot. What can we say about gamma? We know gamma is more than 1. Cp is always more than Cv. Even for an ideal gas, it is Cp minus Cv is equal to an R or R. Therefore, gamma minus 1 is more than 0. Therefore, V1 by V2 is a number smaller than 1 raised to the power positive number. This one must be smaller than 1, right? So this is V1 by V2, for example, is something like 0.5. If you raise 0.5 to the power 8, it's going to become even smaller. If you raise 0.5 to the power 0.8, depending on the value of gamma minus 1, it will still be smaller than 1. It will become closer to 1, but it will still be smaller than 1. So either way, this is smaller than 1. Therefore, P3 is less than P2. And that is what we wanted to prove. Therefore, B lies below A. This is also very interesting because if you calculate the work done on the system, and now you can see, even though it's just expansion work, it's interesting that even though it's purely expansion work, in B, you have to do less work to expand the system. Well, you have to look at design, but there is a difference in the work done. And yeah, it's 0.5 I just made up. It could be anything. I'm just saying 0.005. It doesn't matter. The point being that a number which is less than 1 raised to another number which is, could be anything. And this is why watching the videos is important, because now you will look at the class like notes only and be like, where did the 0.5 come from? What's that? No, it's just an example. So this is always going to be, let's make it 42. Doesn't matter. It's always going to be less than 1. That's the point here. Therefore, B lies below A. So the adiabat lies below the isotope. Okay. So I solved a question. It's time for you to solve a question. Here's a pop quiz. This one's not anonymous. You will not be graded in the sense that it's not going to affect your grade point, but I would like to see how everyone is doing. You have 4 minutes on this one. All right. Let's look at the results. First problem, democracy wins. It's an ideal gas undergoing isothermal expansion. Maybe some of you lost track by getting distracted by the irreversible process, but that doesn't matter. Why does it not matter? Anyone wants to help me? Why does it not matter that the process is reversible or reversible?
Because for an ideal gas, internal energy is only dependent on temperature.
That's correct. But my question for you is, why does, on top of this, it doesn't matter that the process is reversible or irreversible?
Because it's a state function.
It's a state function, correct? You're talking about change in internal energy. And the wonderful thing about that is it doesn't matter whether the path is reversible or irreversible. It depends only on the end states. And like I think Rob said this, the end states themselves, the internal energy depends only on the temperature. So you have 2 end states and both have the same temperature. Whatever path you take, the U will be 0.
If you were trying to integrate over something and you're trying to use that function, you couldn't use it, right? To find the internal energy for the path or something?
It doesn't matter what path you take if you know the endpoints. That's the thing.
Okay.
You don't even have to integrate. You just have to look at the difference between the endpoints, and that's so wonderful. Second problem, democracy lost. Anyone feeling very confident about their answer and wants to help me out?
Shouldn't it still be du equals 0? Because the temperatures, because like delta U is CV dt and the temperature is still not changing.
Okay, have you done the first problem on the third homework?
Yes. Oh.
Then you still think it's true? You derived an expression. So doing this pop quiz problem does not require you to know the first problem on the homework. But if you have done that, we in fact showed, Kevin is absolutely correct. So it might be better actually to go to the third problem and then come back. The third problem, let's do third problem, where most of you got it right. For an isothermal expansion, the average kinetic energy is same, right? We know equipartition. So let's do in pop quiz 3, Ke on an average. Remember, there is a distribution of velocity. So the individual atoms' kinetic energy is different, but on an average, this is proportional to temperature, and equipartition counts the number of degrees of freedom and everything like that. So therefore, delta K is equal to 0. Now let's go back to the second problem.
I don't think you're sharing your screen.
Oh yeah, that's right. I totally forgot. I don't think I can share the pop quiz results or this at the both at the same time. So I will just stick with the iPad. So in the third problem, average kinetic energy is proportional to temperature. Therefore, delta K. Do you all still see the poll results?
Yeah, we can see them.
Oh, cool. So delta K is equal to 0 in the third problem. And in the second problem, we now have to account for delta U. What does delta U come from? Delta U is sum of change in kinetic energy plus potential energy. This is where it comes from. And for an isothermal process, we just showed that for any gas, and so you can also see a hierarchy here. Ideal gas, which is more restrictive than Van der Waals gas, which is even less restrictive. A real gas is least restrictive, ideal gas is most restrictive. A real gas, we already saw that delta Ke is 0 if it's an isothermal process. So this thing is going to be delta Pe. Now, you could have got the correct answer here by 2 ways. You might have remembered that in homework 3, problem 1, Kevin's problem, we showed that partial U by partial V at constant T is equal to A by V squared. If A is positive, this means that partial U by partial V at constant T is positive, right? Which means that U increases as V increases. The rate of increase in U as V increases goes down. This thing is talking about the rate of increase in U, right? As V tends to infinity, partial U by partial V at constant T tends to 0. So this was the mathematical way of thinking about it, but you don't have to remember this. The way I would have done it is to think about a typical potential energy curve. This is not internal energy. This is potential energy, PE. Potential energy curves look like this. Here you are at equilibrium. If you so this is V of R versus R. So potential energy is often denoted as V, right? Confusing with volume, but you know what I mean. So as you increase the volume, the average separation between the particles increases. Therefore, the average potential energy goes up. Therefore, delta PE is positive. And since delta KE is equal to 0, therefore delta U is positive. So du is positive in this case. So 24% of you got it right. So, okay. So the midterm is, this is a good time to talk about the midterm. The midterm will be, let me take a screenshot this, I'll post it on Slack. The midterm is, I think it's easy, but then I have known to be wrong in that. If you're well prepared, you should find it easy. Now is the time to be well prepared. Typically, by the time you get to the midterm, you should know as much as, by the time you get to the final exam, you should know as much thermo as Connor or I. You should be correcting us. You should be perfect in it. So now is the time to get prepared. Be very well prepared, and then you will do fine in the midterm. It will be released as per the schedule online. And it's designed to take, if you're really well prepared, it should not take more than 1 hour. It's a fast midterm. It's not that many problems. And you can use calculator, whatever you want. So it's designed to take 1 hour, but you can take as much time as you wish. Yeah, it will be just like a Gradescope thing. It will be released just on Gradescope, and it's basically 20% of your grade. And the most important thing is 0 discussion. You cannot post any questions on it on Slack. If you ask me something, I will not respond unless I figure out that there is a huge typo that we made, in which case it will be announced to the whole class on Slack and on email. And otherwise, we won't be entertaining any questions. All questions are sufficient. If you think all questions have sufficient information. If you feel there is some information missing, make that assumption and proceed, but think hard before making assumptions. And doesn't the sign of U depend on where you begin and end on the potential distance curve? That's a very good question, Thomas, but where do you expect to start on an average? Here at the equilibrium position, right? It's extremely unlikely that you start from this very, very squeezed state where everything was. So if you just think, most of the potential energy curve is given by this side. Most of the time we are going to stay on this side. You are correct that maybe it depends on you start over here. So in that case, yes, you could have. There is 11 of you who said insufficient information. So if you think that amounts to insufficient information, if that was your reasoning, that you don't know whether you start at this arrow point or this arrow point, in that case, I agree, you're right. But assuming that you started at the equilibrium distance, it is a correct answer. So, but it's definitely, yeah, it's one of these two. How will we get the exam? It's all Gradescope. It's just like a homework where you're not allowed to discuss. That's all there is. Okay, let's proceed. We have to do more practice problems. So now let's stop sharing and let's go to practice problem. Okay, this one asks us to refer to that figure again and calculate the entropy change along path B plus C. So what did that figure say? So PP6, we had a pressure volume curve, and B was this adiabat that we just saw that goes from here to here, and C was an isochore that went from here. here. So this was B, C, adiabat.
I think you're frozen.
Yeah, I am. Sorry about that. I just realized. So B was an adiabat and C was an isochore that took us up. So the B started from P1, V1, T1. It took us to P3, V2, T2. And this is basically the problem that we were doing in class. The whole idea in this was to show that this isothermal path that we had over here that led us to some entropy change. And now we are calculating it instead of A, if we take B plus C, what's the entropy change? So let's first talk about the entropy change in B, delta SB. What can we say about that?
It's equal to 0 since it's adiabatic.
So delta SB is 0 since delta QB is equal to 0. No heat is given. So integral of delta QB by T is therefore also 0. C is the one that is slightly complicated. So let's work through it. In order to do C correctly, so we are interested in delta SC. So what is the change in entropy? That is always given by delta Q reversible, some reversible path divided by temperature. And what is C doing? C is taking us from temperature T2 to T1. It's also changing the pressure, but I'm just going to write temperature up there. Okay. It is an isochoric path. Isochoric means constant volume. What can we say about delta Q reversible in a constant volume process? How much should that be for any gas?
du.
Correct. For any gas, it should be du. Absolutely correct. Who was that? Who helped me here?
I think it was me and
Good.
Elizabeth.
So, okay, good. So this is true in general. And for an ideal gas, what can we say on top of that? CVDT, correct? This is super important. This thing will help you again and again in thermo. So for an ideal gas, this is CV as a function of temperature dt divided by T. Now, one of the wonderful, now this is a nice, well-behaved integral, right? CV is just a function of T, no path function business. Yeah, du is equal to CV dt only for ideal gas. And Caitlin, you should go and practice. Why is that true? Hint is internal pressure for an ideal gas is equal to 0. In order to prove this, we wrote down U as function of volume and temperature, and we did the partial derivative. So du is equal to CV dt. Good point. Du is equal to CV dt for an ideal gas, even if it's not an isochoric process. Remember, but currently we are talking about isochoric process. So this is what we have. Now we can switch the sign of the integral and we can make it minus T1 to T2, CV, temperature T by T. We don't know the value of T2. So we need, and this is where we stopped last time. So we have to do a bit more work to get the value of T2. Let's do that. In order to do that, we will focus on the adiabatic. So, and these PV diagrams are sometimes complicated because even though you are interested in studying the process C, you have to go back to the process B to get the value of T2. And let's see how do we do that. So for path B, it's an adiabat, right? It's an adiabat. What does that mean? That means du is equal to delta W, since it's adiabat, therefore delta Q is equal to 0. In addition, it's expansion work only, so this is equal to minus PdV. And it's a perfect gas, so this is minus nRT by V dV. It's a CV as a function of T, not CV multiplied by T. I will not use brackets if it's multiplication. Why did you make it negative? Oh, I'm sorry, because I flipped the order. So du is equal to this thing, and now it's an ideal gas. So again, we will use our favorite relation, true only for an ideal gas. CV dt is equal to this thing. Therefore, CV dt by T, which we were tackling last time, is actually quite nice. It is minus nR dV by V. And now we can do the integral. We can say T1 to T2, CV dt by T is equal to minus nR dV by V. And what's the volume at T1? At T1, the volume was V1. At T2, the volume was V2. So this becomes minus nR ln V2 by V1. Let's call this equation 4. Let's call this equation 3. Use 4 in 3, and you have a minus sign up front. Therefore, delta SC is this minus sign comes and eats this minus sign, and we are left with a plus nR ln V2 by V1. Therefore, delta SB plus C is equal to plus nR ln V2 by V1, which is the same as delta SA, which we did in class last time. So you can see for an ideal gas, this isothermal process has the same change in entropy for the system as instead of doing an adiabat followed by an isochore. These type of manipulations are kind of at the heart of thermo, and they require you to have a good grasp of the first law of thermodynamics, of when to substitute du with CV dt, when to not, when to use an equation of state. So that's why I wanted to do this problem in class. It's quite fundamental. Okay, any questions about this? Look, it's always going to look more doable if I solve it. Try to do it on your own completely and see how it feels. And that's why I'm gonna skip problem 7. Problem 7, I want you to try on your own. Please try on your own. I would like to see a bunch of solutions, and then I will post. I don't think I will have time to post a video for this one, but I will post the solution and you can look at it. So please try problem 7 on your own, which wants you to go to this path on the top and then coming down, and then you calculate the same entropy change. And that time it is an isobar followed by an isochore, and then you do the same thing. And problem 7, if you really understand problem 6, then problem 7 should be obvious. Otherwise, go back and think about it. Let's go to problem 8. At least one of you had posted it online and you had basically correct idea. So problem 8 doesn't talk about constant volume, constant pressure, constant adiabat, this or that. It's quite a real life problem. This is something you can encounter in any specific setting. How should we proceed in problem 8? Anyone wants to help me? What's the first thing we should do?
Can we establish an equation of state to use first?
Equation of state won't help. Solve for moles of water and copper will help. That's a good idea. But even more fundamental, can we establish that it is a constant pressure process? You just put a bunch of copper in water, probably in a beaker. And I don't think that led to a drop in atmospheric pressure that day. And so it's an okay thing to assume that it is a constant pressure process. So here we will start by assuming constant pressure. It's not a good idea to assume constant volume because that would have required to specify it's a closed beaker. But here what's going to, you might have the water becoming steam or something like that. So it's, in this problem, it's a kind of vague whether it's constant pressure or volume, but I think it's a good idea to assume constant pressure. Then we can solve for moles of water. So number of moles
I
of,
think you're frozen.
oh yes, sorry about that. It's a bad screen share day. So we assume constant pressure and let's solve for number of moles of water. So number of moles of water will be given by, we have how much? We have 100 grams of water and divided by the molar mass of water, which is 18.0152 gram per mole. And we can calculate this, whatever it comes out to. Then we will also write down number of moles of copper. How much copper do we have? We have 25 grams of copper. And as you can see, when you solve these problems, it's a very good idea to write down the units explicitly. Many times missing values, missing numbers, and all this thing about what is equipartition, what is N, these things become completely redundant. If you are being careful with the unit, you won't have to worry about these things. 25 gram of copper divided by the molar mass of copper, which is 63.546 gram per mole, and whatever this comes out to. So the first thing is we assume constant pressure. And the second thing to keep in mind is that the heat lost by copper. Why should copper lose heat? Because the copper is 363 Kelvin, while the water is 293 Kelvin, right? So heat lost by copper is equal to heat gained by water. Why is it fair to say this? It sounds like a naive thing, but am I really justified to say this? It's an assumption. We are saying nothing is lost to the atmosphere, right? So we are assuming here, we are assuming that together the copper plus water is a closed system. Nothing is being lost out of both of them. So, and that's what we need to calculate. We need to calculate the heat lost by copper. And how do we do that? Now we have a constant pressure process. So delta Q will be equal to delta H because it's a constant pressure process for both of them. And we have delta H given by number of moles of whatever we have multiplied by the molar heat capacity. Many a times in the problems I have been using this bar symbol. If you don't use the bar symbol, that's still okay. There is nothing special about it. We know that it is molar heat capacity because that's what the problem has given us. So N Cp bar multiplied by delta T. Right? This is the change in enthalpy. And this is something we have to calculate for copper. So NCu, Cp bar also for Cu multiplied by delta T for Cu is equal to N water multiplied by Cp bar for water multiplied by delta T for water. NCu we just wrote 25 divided by 63.546 multiplied by heat capacity, molar heat capacity of copper, that is 24.5 delta TCU. We don't know the final temperature. That's what we are trying to solve. And we are assuming that the final temperature of water is the same as final temperature of copper. So this is going to be from 363 minus X. We don't know what's final X. This is TCU is equal to T water final. That's what we're trying to solve. This thing is equal to number of moles of water, which is 100 divided by 18.0152 multiplied by 75.2 multiplied by x minus 293. And you have to be careful with that. One of these has 363 minus x, the other one has x minus 293. It's a simple linear equation, a bit of math, and you will get, not even math, just arithmetic, and you will get 1.259 into 10 to the power 5 Kelvin is equal to 427.6x. Therefore, x is around 295 Kelvin. That's the temperature, is somewhere in the middle. The temperature of water did not rise by a lot, right? There are two reasons for that. First of all, you had 4 times more water than copper. And secondly, the heat capacity of water is roughly 3 times more than 3 times more of copper, right? Copper molar heat capacity was 24.5, water heat capacity was 75.2, and the number of moles of water you had is close to 5 moles of water, 6 moles of water, while you have less than a mole of copper. So that's why the effect on water wasn't that much. It just increased a bit. I have already accounted for that, x minus 293. This is the negative sign, which has been absorbed in here. Yeah, exactly, Daisy is right. I have accounted for that over here. Okay, that's PP8. Let's keep moving forward if we have to have any chance of looking at the other problems. Okay, let's go to PP9. What does that one say? That one says, to calculate delta S, if 1 mole of ideal gas is expanded reversibly in isothermally from 1 bar to 0.1 bar, explain the sign of delta S. It doesn't specify whether it's delta S system or surrounding, but in the next part, it tells you calculate delta S surroundings. So this means that basically in part A, you were calculating delta S surrounding. Otherwise, this thing needs to be stated clearly as to what is the delta S that you're calculating. And in C, you have to do both A and B for isothermal expansion occurring in vacuum. So let's look at first part. So delta S if 1 mole of ideal gas is expanded reversibly and isothermally. So it's an isothermal reaction. What does that mean? du is equal to 0. Again, why does that mean so? Because it is isothermal for ideal gas. You just saw in the pop quiz today and in homework 3 that this is not going to be true for in general. It's an ideal gas, therefore du is equal to 0. What does du mean? This means delta Q minus PdV is equal to 0. Therefore, delta Q is equal, I again did that funny symbol, where I did this on top of that. No, I did that. Delta Q is equal to PdV. For an ideal gas now, we can say PV is equal to nRT. Therefore, V is equal to nRT by 1 by P, right? And we are talking about an isothermal process. Therefore, these things can be treated constant, the nRT by P. Just checking if my screen is still not frozen. Yeah, it's not frozen. So what does this mean? This means therefore dV is equal to nRT d of 1 by P, right? Is equal to minus nRT dP by P squared. And now nRT is equal to PV. So this is equal to minus PV by P squared dP is equal to minus V by P dP. Therefore, delta S, which we need to calculate, is going to be pressure. Let's go carefully. Delta S is going to be delta Q reversible by temperature. Delta Q reversible is PdV. So this is integral PdV by temperature. And we just, now we can substitute, do we have a value for P by T? So P and dV, we just showed that dV is minus V by P dP. So this is integral P by T dV, which is minus V by P. Again, the way I'm solving this problem, it might look a bit confusing. This is not the only way to do this. This is one way to do it. You might have a simpler way, but this is one way to do it. The nice thing here is pressure cancels. We are left with minus V by T dP. And minus V by T dP, again using equation of state, is minus NR. Well, the minus stays outside. So this is NR by P dP, and now we can integrate, and it's quite simple. Why did we do this? Because the question talks about change in pressure. So we brought everything to units of change of pressure. So this is now minus NR ln P2 by P1. And what is the value of P2 by P1? That is 0.1, right? It went from 1 bar to 0.1 bar. So the answer here is, I should have gone on the left side, but so this is plus 19.1. Why am I squeezing that corner? Let's go over here. So
Professor, I think we can't see the bottom of the screen.
I will. How about now?
Yeah, it works now.
Oh, thanks. Sorry about it. I don't know why I was squeezing in there. So this is plus 19.1 joule per Kelvin. Entropy of the system went up. How about the entropy of the surrounding? So this is delta S system. What can we say about delta S surrounding for this process? Anyone wants to help me? This is part B.
The delta S of the surrounding has to have gone up.
Are you sure? I want a number. It's an isothermal process, right? So delta S surrounding will be delta Q surrounding divided by temperature. That is exactly the same as we wrote over here. Delta S surrounding, all of this is the same thing with a minus sign. This is minus delta Q system by temperature, and everything else here onwards is the same as we did earlier. So this is minus 19.1 joule per Kelvin. It's a subtle point, and we are going to visit this again after the midterm, that system and surrounding together are closed. Yeah, it's in this case, it's closed. Elizabeth is asking, is this always true? Well, you will see in part C, it's no longer true. But in part B, this is true. Because, so let's meditate a bit more over this. What did we do over here? We just said that delta Q system plus delta Q surrounding is equal to 0. Because together, system and surrounding is always isolated, right? The heat that went into the system must have come from the surrounding. That heat that went out of the system must have gone into the surrounding. So that's why delta Q system is equal to minus delta Q surrounding. And it's an isothermal process, the temperature is constant, so we could do everything the way it is. So the thing now is that delta S net is equal to delta S system plus delta S surrounding is equal to 0. So this process is neither reversible, it's not a spontaneous process. Its reverse is not a spontaneous process. This is our definition of a reversible process. The whole thing happened reversibly. It's a reversible process. In part C, and I'm going to finish with this one, and then the last problem I would like you to try, and I will post a solution later. So in part C, we are told do A and B for isothermal expansion occurring freely in vacuum. So Okay, let's leave this one to think and post, and I will post my solutions to problem 9 part C and problem 10, as well as problem 7. These will be posted in Google Drive. I don't think I will do the video, unfortunately, this time because it's too much going on right now, but I will definitely post the solutions and you can ask me about it. Will be posted in Drive once you have posted your solutions online. Okay, so I will see you Wednesday. We will be covering some more new material and that will be important for the midterms. Please, it's not going to be completely new, but it will be the kind of things, becoming familiar with that material will help you in the midterm. Yes, I have office hours at 11 to 12. Okay.